to simulate TORPEX. Then we're going to have a half-hour break, and then Michael Barnes is going to be giving a short 20-minute talk with 10 minutes for discussion, and then Bill Dotton will finish up the day with his own talk on his MRX modeling. Right?
Okay, so here we go with another experiment. During my talk, I will address the following question. First of all, why TORPEX has been built, and what can we do with this experiment. The second question that I will address is how can we approach the study of its dynamics? What are the turbulent regimes that are found in this machine? I will talk also about the comparison between experiment and simulation. And finally, I will have a few slides where I will try to point out what we are really learning from this simulation, what are the implications for all the other systems that we know and the kind of simulation that the rest of the world is doing. So, why TORPEX has been built? Well, we have had a number of talks in this week about how complex of a phenomenon is turbulence in the edge. So let's focus on the scrape of layer region. This is where magnetic field lines are open. Well, it's for sure a region where the magnetic geometry is particularly complex. It's coupled with the core region. There is a lot of sheath and atomic physics involved here. And well, the plasma is a bit cooler than in the core region, but experimentally it's still difficult to access. One cannot stick probe into it, it's still too hot. So there is for sure the need of a basic plasma physics experiment that can help us uncover the physics of this region. This is why the TORPEX experiment has been built as a paradigm of turbulence in the edge. So TORPEX is a relatively simple configuration. It's called the simple magnetized torus. It's a toroidal device where the magnetic field has only two components, the toroidal component and the vertical component. The result is that magnetic field lines have a helicoidal shape that winds around the magnetic field and terminates on the bottom and top part of the vessel. Now, if we give a look at this configuration, well, the field lines are open, so there are parallel losses at the end. There is magnetic curvature. Now, plasma is produced by injecting microwaves and exciting electron at the electron cyclotron and upper hybrid resonance layers. Now, this source region is radially localized, so this triggers plasma gradients. And if we think for a second, parallel losses, magnetic curvature, and plasma gradients are the fundamental ingredients, fundamental elements of scrape of layer turbulence, which are presented here in a much simpler configuration. So the big advantage of TORPEX is that the plasma is relatively cold, so one can stick probe into it and get very detailed measurement of the dynamics. Here is, for example, one of the probe that samples TORPEX turbulence, and here is one of the results which shows turbulence in a cross section. Now, just to give an idea, plasma is produced in this source region, and this is the kind of measurement of visualization that we can have for TORPEX turbulence. So basically, in a few words, measurement of all relevant plasma and field parameters can be obtained in this machine. So what are the properties of TORPEX turbulence? Well, let me say that they are very similar to what we see in the edge. First of all, the fluctuation, there is not a clear distinction between fluctuation and equilibrium. Actually, they have the same order. Also, the scale length of the equilibrium are comparable to the fluctuation scale length, and they are much longer than the ion Larmor radius. There are also some other things that it's safe to assume and which actually simplify quite a lot our simulation, and that the ions are pretty cold. plasma beta is small, low frequency perturbation, parallel scale length much longer than the perpendicular one, and the plasma is fairly collisional.
How collisional? I mean, like very collisional?
Moderately collisional. Moderately up to the point that one can use a fluid model for its description. So a Braginski kind of model. Now there are all a set of assumptions that we can use, and we can get back to the electrostatic drift reduced Braginski equation. Just probably everybody's familiar, but just to, what is the physics in this equation? Here is just the density equation, the continuity equation, which contains a term related to the convection, E cross B, drift. There is a diffusive term due to some amount of collisions, a term related to the compressibility due to the curvature. There is a parallel dynamics and a source term. And then we have similar equation for temperature and for the vortices, similar ingredients. And we use a parallel momentum balance to get the electron and ion parallel velocity, and then the vorticity and the electrostatic potential are coupled with a sort of Poisson equation. So what we have been able is to make...
So you have no neutrals in that equation?
Non-neutrals, no, they are not. Let's say, as you said, in the first order approximation, they would enter into vorticity equation as a damping extra term, but it's not included here. So what we have done is to basically write a code that is able to solve this equation in the full TORPEX domain, being able to evolve both the equilibrium and fluctuation as a result of a balance between source, parallel losses, and perpendicular transport. And here is the typical movie of the potential in this electrostatic potential in this machine. So plasma is produced in this region here that is basically toroidally symmetric, and then a number of instabilities starts and are triggered, which lead to transport to the low field side of the machine. So what is the character of TORPEX turbulence? Well, let me first say that it strongly depends on n, the number of field line turns of the machine. So here is an example, a practical example, n equal to 2. So the field lines goes twice around the device. Now, how does it depend? Well, experiments show that at low n, so few field line turns in the machine, turbulence is characterized by k parallel equal to 0. When n is increased, what experiments show is that k parallel becomes different than 0. What theory and simulation that I am going to discuss have shown is that in the first case, the simulations are dominated by an ideal interchange mode, while in the high-end case, the resistive interchange mode is the one that drives turbulence. Let me also say, and we'll come back later to this, is that drift waves, which before were thought to have an essential role in this machine, are actually shown to be likely inaccessible in this condition. So just a little bit of algebra. So how about, let's start with the low n case, where k parallel is one observed that k parallel equal to 0 turbulence, which is an ideal interchange mode. How can we describe it? Well, we have an equation for temperature and density, which we can sum up at the leading order terms. They're reduced to the convective term. And then we have the vorticity equation that for k parallel equal to 0 can be simplified as a balance between the polarization current and the curvature drift. So, well, we can linearize this system, and one gets that the system is unstable to the ideal interchange mode whose growth rate is given by this expression, which depends on both the pressure scale length and the radius. Now, how does a k parallel equal to 0 perturbation look like in here in a configuration like TORPEX? Well, let's introduce a couple of notation. One is LV, the full height of the device, and the other one is delta, which is the return distance of a field line on the poloidal plane. Delta so is equal to LV, the full height, divided by n, the number of field line turns. Okay, now we can ask, in the case of k parallel equal to 0, what's the possible longest vertical wavelength that is allowed in this system? Well, if you think for a second, if things should not depend on the field line, then if k parallel is equal to 0, then the maximum allowed wavelength should be equal to delta, LV over n. One cannot have bigger modes that extend on longer wavelength in the system. And actually, experimentally, TORPEX experimental data show that this is the case. So here I have plotted the experimental data of the inverse of the vertical wavelength that is measured as a function of the number of field line turns. And as you can see, there is a linear relation between 1 over LV and n, pointing out that lambda v is equal to LV over n, as we were expecting for k parallel equal to 0 turbulence. Then, suddenly, at some point, the lambda v increases. Actually, one observes that this goes to value of 1. In this regime, it's measured that k parallel is different than 0. And actually, as we will discuss later, this is shown, it's shown that in this case, the resistive interchange mode dominates turbulence. So, how does it look like ideal interchange turbulence in our system? Well, here is a case where there is n equal to 2. So if k parallel is equal to 0, we expect basically that one wavelength in the system, one wavelength occurs in half the full height of the device. And this is actually what is shown in this movie, where you see clearly that the wavelength in the system is half the height of the device. And maybe a clearer movie is this one that shows again the potential, electrostatic potential in two cross sections and in one parallel plane that winds around the torus. So, as you can see, there is clearly a two wavelength in the system. And also you can notice that the dependence along the parallel coordinate is very weak. K parallel is pretty much equal to 0. So what happens when n becomes bigger than 7? Well, we start to see that k parallel start to be different than 0, and exactly that the wavelength of in the system reaches the global, the full height of the device. So why is that? Why does it occur at n equal to 6? One other observation is that turbulence becomes toroidally symmetric. Why is that? So that's what we are going to explain. But let me first point out that this feature is captured by the simulation. So here is again a simulation where n is equal to 16. As you can see, in this case, the turbulence is toroidally symmetric. The vertical wavelength is equal to the full height of the device, as we see from the simulation. If these were dominated by ideal interchange instability, we would have a wavelength that will be 1/16 of the full height. And well, here again is a movie that shows again in two poloidal cross section and in a toroidal cut. Is not anymore a parallel cut. And as you can see, maybe better, turbulence is toroidally symmetric, perfectly toroidally symmetric, and that the wavelength in the system occurs is equal to the full height of the device. So how can we describe this mode? Well, we have to introduce, with respect to what we did before, k-parallel, finite k-parallel term. So, okay, at the first order, the density and temperature equation do not change. At the intervorticity equation, now we have to add a term related to the parallel derivative of the parallel current. And then we have to close somehow, to get somehow J parallel, and we do that by using Ohm's law, the simplest possible, just a resistive Ohm's law. What we get is that there is still an instability in this system whose growth rate is equal to the ideal growth rate that we have seen before, but which is corrected by k-parallel terms. Now, this term actually decreases the growth rate of the ideal with respect to the ideal interchange growth rate. So, if we want to have a fully developed instability, this term has to be smaller than this one, which what if we do the algebra, we see that this occurs for k parallel over k perp that is smaller than a certain quantities that depends, let me point out, on the resistivity. Or also we can write as if the resistivity has to be bigger than a certain value that depends on k parallel over ky over k vertical. So there are two cases here. One is the case that we have considered before, k parallel equal to 0, which can exist whenever and does not require any resistivity and whose growth rate is always equal to the ideal interchange growth rate. And then there is the k parallel different than 0 instability, which actually requires a finite resistivity. So what are the parameters of this resistive interchange mode in a configuration like TORPEX? Well, let me express k parallel as a function of the k vertical and the k toroidal. So the vertical wave number and toroidal wave number. And let me introduce also the vertical mode number L and the toroidal mode number N. Well, if you substitute these here, well, after 1 second, you see that k parallel can be expressed as a function of the vertical mode number and the toroidal mode number, as well as the ratio between k parallel and kV. Now, what the resistive interchange mode requires is that k parallel over kV is as small as possible, and it should be smaller than a certain quantities related to n parallel. When does it occur? Well, this occurs actually, if you look here, k parallel, the smallest possible k parallel for big n occurs in the case that n is equal to 0, so in the case of toroidally symmetric turbulence, and when L is equal to 1. So in the case that the vertical wavelength of the system is equal to the height of the device. So what does it mean? It means that plug in this number, that we can have an expression, a certain expression for k parallel. kV is dominated, so the vertical wavelength is equal to the full height of the device, and well, if we plug the numbers in for k parallel and k perp in this relation, we observe that n, so the number of field line return, should be bigger than a certain expression. So why is there a transition from ideal to resistive interchange for passing from low to high N? Well, there are two reasons for that. One is that, as we have just said, the resistive interchange requires high N. The second one is that actually the ideal interchange requires low N. So, in fact, if we increase N, the vertical wavelength in the system decreases, and also K vertical increases. Now, there is one can show from the linear relation that the mode becomes stable when K exceeds a certain threshold. And also transport becomes less effective at high K. If we plug the numbers for TORPEX, we find that threshold should occur at N about 10. So here is the plot that summarizes all these findings. So we have plotted as a function of the number of inline returns and the steepness of the gradient, density gradient, what is the vertical mode number of the fastest growing mode. And as you can see, above a certain N, the L is equal to 1. The system is dominated by the resistive interchange mode. For low N, the linear theory shows that L is equal to N, as we expect from K parallel equal to 0 mode. Well, let me point out let me talk about the resistive drift wave. This was an instability that was thought to have an essential role in this machine. Well, the easiest way to get this instability, to get the essential properties of this instability, is to neglect curvature in this system, sound waves, and electron inertia. And one gets the equation that describes the resistive drift wave, which are shown to have a gradient, growth rate that is of the order of omega star, I mean CS over LP. The K per pro S is about 0.5, and there is a certain K parallel of the peak growth rate. Now we can define the drift wave regime as the regime where the growth rate, the linear growth rate of the drift waves is much bigger than the ideal growth rate. Now this occurs, well, if as we've seen, the growth rate of drift waves is inversely proportional to the pressure gradients, while the ideal growth rate of the resistive of the ideal interchange mode is related to the square root of LP. So drift waves basically, in order to grow, requires a much steeper gradient than the ideal interchange. And one can plug the number and get that actually the gradient required by drift wave is very steep. We can see that in this phase space diagram, where actually there is a drift wave region. But now if we think about the full system, well, when the gradients are steepening up, there are modes like the ideal and the resistive interchange that can drive a lot of transport and prevent the steepening to the drift wave regime, which so results to be inaccessible.
But when you say people thought that the drift waves were going to be important, that was before it was built, or just some kind of intuitive belief because there were density gradients? Or
Right. There are a number of experiments of these kinds around the world. One is Helimac that I'm going to talk right now, which is at the University of Texas. And there is actually a paper describing and comparing drift wave theory with drift wave measurement in this device. And then actually in TORPEX 2, before getting to this global simulation and seeing that it was a resistive interchange mode, people actually thought that it was a drift wave. So K parallel different than 0 was immediately associated to drift wave. And also another, there was an experiment called Blaman, which was at Tromsø. Now I think they are rebuilding it at West Virginia, if I am not wrong. And there were also strong claims that turbulence with k parallel different than 0 was due to drift waves. So, okay, let's go to the other, one other experiment that we have approached, which is HILIMAC. HILIMAC is at the University of Texas, and well, it's fairly similar. The big difference between HILIMAC and TORPEX is the height of the device. That in TORPEX is 40 centimeters, in HILIMAC is 2 meters. So one can redo the plot, and what can we find? Well, we find that there is an ideal interchange regime, a resistive interchange regime, L equal to 1, and then, well, this was a sort of a big surprise too. There is a new mode, which we haven't been able to characterize fully, which it's a non-MHD drift interchange mode. Let's see, how does it look like? Well, let me just point out that this mode grows with k per pro s about 1 for adiabatic electrons and has k parallel different than 0. So the minimum model in order to describe this model is this one. So can be obtained with no resistivity, no electron mass, Ti equal to 0, and Vi is not necessary. Now we have to take into account curvature in the vorticity equation and parallel derivative of the current. In the density equation, one has to take into account compressibility terms, as well as in the temperature equation, as well as the parallel streaming, and well, Ohm's law give adiabatic electrons. So if we sum up everything, well, we get a dispersion, a quadratic dispersion relation with a growth rate that is about the ideal growth rate, but which occurs at k per pro s of order of 1.
Sorry, if you keep TE just constant there and don't use the temperature equation, how different is
The mode disappears.
disappears altogether?
Yeah, right, Barrett.
Yeah, it's driven by the temperature gradient stabilized by the density gradient. I don't know what this mode is. I've never, I don't know the name of it. We have labeled it.
Yeah, non-MHD.
For non-MHD, you have to interchange, right?
Okay, so this was a big picture to show what we have learned from TORPEX and what the simulation have shown. But let's try to get to the bottom of it. So what are we really learning? Is this important for other systems or not? Well, of course, we are learning how to characterize turbulence in a relatively simple system. But we are learning also something else. First of all, the need of global simulation. For example, flux tube simulation will not be appropriate to describe a certain set of instability. For example, the resistive ballooning mode, the resistive interchange mode. And then we have also learned about the need of non-local simulation. For example, for the saturation mechanism. And what we are also learning is how it's possible to perform comparison between experiment and simulation. So let's go, maybe I'll talk about these 2 points, the need of these 3 points, the need of global simulation, need of non-local simulation, and how to perform comparison. So, need of global simulation. Well, the first attempt to simulate TORPEX device, a three-dimensional attempt, was through a flux tube simulation. How does it look like, a flux tube in this configuration? Well, the flux tube is something that winds around the device, goes like that. So you can make the usual approximation of flux tube, periodic boundary condition here and here. One does not need to do that in the perpendicular, but basically periodic boundary condition here and here. And so one can develop this and basically do the simulation in a sort of this system. Now, if one looks at how the turbulence looks like in this system, when the vertical field is decreased and n, so n is increased, basically the flux tube becomes narrower and narrower. Well, what is observed is that actually, well, in low n case, so high BV, turbulence, which is k-parallel, is still pretty well described. And one sees the similar structure of the ideal interchange mode that we have discussed about. But for high value of n, actually, well, we cut a mode, we eliminate one big global mode from the system. So the drive of turbulence in this system is reduced with respect to the real configuration. And actually what one observes is a steepening of profiles and increasing of shear flow that actually is not seen by changing n in the experiment. Then let me point out also the need of non-local simulation. Well, we have what we have done is trying to estimate the radial transport with an analytical estimate. Now, how can we were based this calculation on two-dimensional simulation. So how can we do that? Well, the particle flux will be given by the average of the density fluctuation and the radial E cross B. So how can we estimate those? Well, density fluctuation. Well, what is driving the instability here is the density gradient. So the transport the instability will saturate when the instabilities has been able to flatten the density, the equilibrium density gradient, which can be written in this way. So basically that the fluctuation, the gradient due to the fluctuations should be of the order of the equilibrium gradient. So if we express the fluctuation, we can write as a function of n naught, the equilibrium density, and the equilibrium density gradient. And we have a Kr, so which is the typical scale length of the fluctuation. Now the thing is that Kr is occurs on a scale length that is intermediate between the mode, typical mode width, and the equilibrium scale length. Now in flux tube simulation, these quantities ordered out. And well, one can do the same for the fluctuation of the electric field, just to estimate, and this one can use the continuity equation at the first order and get a relation between delta phi and delta n. Well, at the end, one can get an analytical estimate of the particle flux as a function of equilibrium quantities. And well, just to be sure, we can compare with simulation result. So here is the analytical estimate, and here is the simulation result. And if things have been done right, they should follow, points should follow here. And well, actually, what do we see? We see that there is a set of simulation where this occurs. And well, there is a set where actually the flux is reduced, measured in the simulation is reduced with respect to the analytical one. And why is that? Well, this is when the E cross B becomes important, but we did not take into account that in the analytical estimate. So the last point is how can we make experiment and simulation comparison? Well, what we have pointed out is that a comparison has to be performed by using observable, by using quantities across different hierarchy levels. I mean, it's not possible to compare simulation and experiment just by looking at the level of transport, because maybe the properties of the instability that drives this transport are different in the two. So one has to do a comparison at all the hierarchy levels, starting from the, what are the linear instability, the properties of the linear instability, going up to transport level and diffusion. And then a composite metric that takes into account the agreement of each observable has been introduced, as well as we have also introduced a quality factor that defines how good is the comparison between experiment and simulation. The idea is that if one does a simulation between a comparison using comparing 10 quantities is much more valuable comparison than using just one quantity. And so we have applied this algorithm to compare experiment and simulation, and we have used the 2D simulation and a set of 3D simulation varying n. Here is a complete disagreement, and here is what I will call perfect agreement. Well, so what we have seen is that 2D simulation becomes really bad at high n. In this case, in fact, the k-parallel becomes different than 0, and 2D simulation are not good, while 3D simulation remains about good, I mean, reasonably good. So to get to the concluding remark, so what are we learning from TORPEX? So we have been using simulation that evolved both plasma equilibrium and fluctuations, and showing that it's actually possible to interpret experimental result. Now, we have seen that turbulence is subject to a number of driving mechanisms, which is a competition between ideal interchange, drift waves, and resistive interchange. And the properties of plasma turbulence reflect different linear drives. Now, we have talked about Helimac, but also LAPD. There are similar analyses can be carried out in other basic plasma physics experiment. But the important point is that TORPEX is providing an ideal test bed to study techniques and assumptions that have to be used for plasma, or have not to be used for study plasma edge turbulence. And just to say what is next, well, here the code that has been used for TORPEX simulation has been developed with to study scrape of layer simulation. These days Barrett and I, we are looking at first simulation, and this is just to give you an idea of how the scrape of layer simulation look like. And with this I have concluded. Thank you for your attention.